All right, this is part 2 of logarithmic properties, and in this problem, notice here, or these problems, we're going to be condensing. Condense each logarithmic expression into a single logarithm. And so what you're going to find is we're really doing what we were doing previously in reverse. These aren't quite as long and complicated, but you get the basic idea. So now we have 2 or more logs, and we're going to condense these into one. And you can see I've written the properties at the top right over here. So let's go ahead and get started. Notice we have the log of 54 minus the log of 6. So we are going to be using the second property here, the quotient rule. And so this is the log of 54 over 6, but 54 over 6 is 9, so this is the log of 9. Now on number 15, you've got to be careful here, again, as far as the order you go. Notice we have a sum of logs, and so we're going to end up using the product rule. Basically, we're going to start on the right side and go over to the left side. The only problem is, notice these are ones out in front, and on this problem those are not ones. So if there's numbers out in front of the log, you cannot use the product rule and you cannot use the quotient rule. The only rule I can use here is the power rule. So I'm going to go ahead and use property 3, and I'm going to move those numbers out front to become powers. This becomes the log base b of x to the 5th plus the log base b of y to the 6th. Now I can use the first property, which is the product rule, and we can, since we have a sum of logs, we can write this as the log of a product. It'll be, we're using property 1, it'll be log base b of x to the 5th times y to the 6th. All right, so 16 is similar to the one we just did. Notice we have these numbers out in front. We're going to use the quotient rule because of the minus here, but we can't use it until we get those numbers out front out of there. So let's go ahead and use property 3, and we'll move those to be exponents. We get the natural log of x plus 3 to the 1/2 power minus the natural log of x squared. Now notice I didn't change this from a minus. I could have made this x to the -2 power and wrote plus instead, and it would work, but I find it's easier to just keep the sign the way it is. So all we're doing is moving 2 to be an exponent. And now notice what we have here. This is the square root of x plus 3, and normally we would want to write it as a square root in our final answer. So we're going to go ahead and use the quotient rule, property 2. So this is the natural log of the square root of x plus 3 over x squared. All right, I would encourage you to maybe try the next 2. If you can figure those out, then I think you're doing pretty well. All right, let's see how you did. So on number 17, we start the same way. We're going to move those numbers out front to be exponents. Now notice we have a sum of logs, and we're also going to have a subtraction of logs. And I'm just going to work my way from left to right. And so this, we're going to go ahead and use the product rule, property 1. And this becomes the log base 3 of x to the 4th times y to the 7th. And then don't forget we have minus log base 3 of z cubed. And then this can be written as using the quotient rule. So now we can combine this into one log. It'll be the log base 3 of x to the 4th times y to the 7th over z cubed. Now I want to show you something here that's kind of interesting, and it's something, I know some of you might have been able to go from here right to here if you see a pattern. There's a nice pattern here. Notice that this is a plus out front, it's positive log, and that x to the fourth ended up in the numerator. Notice here you have a plus, and the y to the seventh ended up in the numerator, in the final answer. Notice this minus here, and our z, oh, I think that's, yeah, that's a z cubed. I wrote that wrong. Oops. And that z cubed end up in the denominator because of that minus being out front. So that's a nice pattern. You can actually go from there to there if you see that pattern. I did it in 2 steps. All right, let me fix that. Okay, let's go on to number 18. So here, this is the log of a quotient. Now you might be tempted to try to do something with the x squared minus 9 or the x minus 3. See, this is a difference. It's the log of a difference. It's the log of x squared minus 9, or the log of a difference. See, we don't have a rule for that. We have the log of a product. Oops, let me change colors here. We have the log of a product. We have the log of a quotient. And we have the log of something to a power. Those are the only properties we have. We don't have anything for the log of a difference. And so you've got to be careful that you don't do something that we have no property for. These are the only 3 properties we have. All right, so here, only thing I could do is use property 2. This is the log of x squared minus 9 over x minus 3. We're just using the quotient rule. Now, hopefully you notice the numerator is a difference of squares, and that can be factored as x minus 3 times x plus 3. And of course, our x minus 3's cancel, and you get the log of x plus 3. And again, this is not the log of a product, it's not the log of a quotient, and it's not the log of a power, so there's no log property that we can use, and we're done. All right, 19 is just another similar example to what we just did. So I'd encourage you to try that one and then watch the video. All right, so first of all, you should have used the quotient rule, and notice the numerator and denominator factor here. So I need, using the AC method, I need 2 numbers that multiply to negative 14 and add to negative 5. Of course, that would be 2 and 7 with a negative 7 and a positive 2, right? Because negative 7 times 2 is negative 14, and negative 7 plus 2 is negative 5. In the denominator, we'll get x minus 2 times x plus 2. Our x plus 2's cancel, and so we end up with the natural log of x minus 7 over x minus 2. All right, let's move on. We've just got a few more problems here. In fact, 20 through 22, we've already done problems similar to these, but we're going to go ahead and take advantage of some of our new properties that we have, actually just one of them. It's going to be the power rule. So notice in the first one, we can use the power rule, and we can move that 5 out front, and we get 5 times the log base a of a. Now remember, a logarithm like this can be simplified. A logarithm is an exponent. This is the exponent you put on a base of a to get a. Well, that would be 1. A to the first power would be a. So this is 5 times 1, and we get 5. Now 21 and 22 are almost exactly the same, just a little different because we're using a couple of other ideas. On 21, remember this is, well, first of all, we'll use the power rule again, and we'll pull out that 3. But this is a natural log, which has a base of e. Whoops, let me back up here. So remember, the base here, whoops, let me change colors. the base here is e. So the question is, this log is an exponent. It's the exponent you put on an e to get e. Well, that would be 1. So 3 times 1, we end up with 3. Now on 22, the first thing you should have done is written this as the log base b of b to the 1/3 power. So here you're asking yourself, well, actually we can move that exponent out front, and we get 1/3 times the log base b of b, and again that's going to be 1, and so we end up with 1/3. All right, I would challenge you to see if you can figure out what 23 is equal to. You have to really look at this log and think about what that number is. And if you can reason it out using the things we've discussed about logarithms, hopefully you can see what this equals. Anyway, I'll tell you in a sec. All right, so hopefully you had a chance to think about it. So this is 5 to a really interesting power. Now remember, a logarithm is an exponent. This exponent is the base you put on a 5, or it's the exponent you put on a base of 5 to get 2x. But we're putting it on a base of 5. And so this actually does equal 2x. Whoops, let me go back here. So this is equal to 2x. Now, so I'll say it one more time. This exponent is the exponent, this logarithm represents an exponent. It's the exponent you put on a base of 5 to get 2 times x. Well, we're putting it on a base of 5, and so we're going to get 2 times x. Now, what if you don't see that? What if that doesn't make sense? Let's just say 5 times the log base 5 of 2x is equal to a. Well, this is an exponential equation, base, exponent, answer. So let's go ahead and write this in log form. It'll be log base 5. The answer in the exponential form is a, and so that goes here. And the logarithm goes on the other side. Remember, it's base, exponent, answer. All right, so now you can see that these two logs are equal, and they both have base 5 as their base. So wouldn't it make sense that a and the 2x must be equal? So a equals 2x. And so our answer is 2x. All right, so I would encourage you to try 24. It's essentially the same problem, just a little different. All right, if you said 4, that is correct. So remember, this is the logarithm you put on a base of 10, because it's a common log. It's the exponent you put on a base of 10 to get 4. Well, we're putting it on 10 on a base of 10, and so we would get 4. Again, if you're not seeing it that way, you could say, okay, it's a. Call it a. This is exponential form. You have base, exponent, answer. So let's go ahead and write this as a logarithm, the logarithmic form. We have log base 10 of a equals log of 4. Now these are both base 10 logs. I'm going to go ahead and write them so they look the same. And so you can see these two logs are equal. They're both common logs, or base 10 logs, which would indicate that a must be 4 in order for the two logs to be equal. And so our answer is 4. Okay, and that's the end of this video.